Hey there, this is Debesh, the info security researcher. This is the third part of the online mini workshop on computational photonics. The title of the part 3 is Real-Time Propagation of Light in Complex Media. And the speakers are Professor James Cole and Dr. Saswatee Banerjee. So without any other words, I will just hand over the platform to Professor Cole and Dr. Banerjee. Please.
Yes. Hello, good evening. Depends on which time zone you are in. We are in the Washington, D.C., where it is about 11 in the morning, and wherever you are, so good day, I should say, whether it's the dark or light outside. All right, so today I'm going to present the non-standard finite difference time domain methodology for the simulation of light and microwaves in nonlinear materials. Now, I think some of you may understand, have heard of the finite difference time domain methodology, but maybe you might not have heard about the non-standard finite difference time domain methodology. So the non-standard is basically very similar to the ordinary fdtd, finite difference time domain, except that it is the parameters are slightly different, and this difference in parameters makes it much more accurate and actually somewhat faster. And I'll show you some of the details. But first of all, I'd like to go to next page down. So I'd like to give you some background about nonlinear Maxwell's equations. So I'm going to use some unconventional units that make the equations a little bit simpler. So I'm going to use units in which this is the electrical permittivity in vacuum, and I assume you understand what that is. It's basically a parameter which governs the speed of light in vacuum. And I'm going to define it this way. And this chi1, chi upper 1, is something that it's a constant. You can just think of it that way. And then the magnetic permeability, again, it governs how magnetic fields penetrate the vacuum. And then this is the speed of light. C is the speed of light. And so we're going to take these to be constant. They can actually vary. The epsilon, the electrical permittivity, notice that here is epsilon and here is epsilon 0. So this is vacuum and this is in the material. And perhaps you have seen something like this. The electric displacement, let me go back here. The electric displacement is the electric field that results from the material. And so it's the original electric field in vacuum, and then it has some nonlinear parts. There's a linear part where this is the reaction of the material, chi1 times E, and then a nonlinear part, and I'm going to take that, I'm not going to consider higher orders. It will be chi2 E squared. So this is where the nonlinearity comes in. You can go to E cubed terms and even higher, but E squared and E cubed have been the ones that are most important for a lot of the technology of nonlinear materials. And a very familiar, for those of you who may not be very familiar with this, but a very familiar everyday example, you probably have a red laser pointer, and perhaps you've seen a green one. The green one is exploiting nonlinearity in the material of the red laser. All right, so let's go to Maxwell's equations in a nonlinear material. So you often would see this written with D being epsilon E. Here we cannot take the epsilon out immediately. So we have this is the familiar form, and then we have this, and then finally we get Maxwell's equations in the nonlinear material, and this is the index of refraction, N is index of refraction, and we have this nonlinear term. Now, I'm going to just do this in one dimension because it will be much easier to illustrate the principle, but we can very easily extend this to 2 and 3 dimensions. Now, I'd just like to remind you, you might say, well, there are 4 Maxwell's equations. One of them governs the divergence of the magnetic fields, and that is automatically covered. That is automatically as a result of this first Maxwell's equation. And then the other equation that you might remember is that the divergence of D is often equal to 0, or the charge density. We're dealing with a material where there is no charge, no free charge. But in a nonlinear material, in a linear material, if there is no free charge, the divergence of E is equal to 0. But in the case of nonlinearity, it's not necessarily. But if the nonlinearity is small, then it's a pretty good approximation. So this is so we can assume that this is actually true, even though strictly speaking, it is not quite true. All right, so this is what we want to solve. So this is a nonlinear wave equation. If the other side, if the right side were 0, this would be a linear wave equation, and then there are many methods to solve it. There are actually analytic solutions if there are no boundaries. If there are boundaries, then you do need a numerical method, such as fdtd, the finite-difference time domain method. So I just want to say a few quick words about the standard model and the non-standard model of a differential equation. So basically, in the standard model, we take the parameters of the differential equation. So for example, right here, we would take these parameters and put them into the difference equation. But in the non-standard model, we change these parameters a little bit to make it more accurate. And I will, in a moment, show you how this is done. So again, I'd like to just give a little bit of background material about finite differences. I went through all of graduate school for the PhD in physics, and I didn't worry too much about difference equations. Of course, you would have seen this in elementary calculus class where the h goes to 0. And maybe you might have seen this and maybe the central difference, but at least I didn't worry about it too much because we were solving equations analytically. At least all my professors who were much older than I was thought that everything could be solved analytically. All right, so we can, for the purposes of this talk, I'm going to define some difference operators just to make the notation simpler. And so the first one is this central difference operator. And then if you apply it twice, you get this. And this is what you should remember because I'm going to use this very often, this dx squared. So this is a finite difference, a double finite difference, and it comes out to this. And I'm going to apply it to both time and space. So here is what we're going to need mostly, the second derivative with respect to something. And so it comes out to this operator right here. So I'm going to write it this way. So I'm going to write that dx squared, partial dx squared, is this finite difference operator divided by delta x squared. And I'm going to do the same with time, as you will see. All right. So first of all, let's look just to introduce the finite difference time domain method. let's look at the ordinary wave equation. Before we go into the nonlinear one, let's look at the ordinary linear wave equation. So we replace the partial derivatives with finite differences, and we get an equation that looks like this. This is a difference equation model of the wave equation. And then we solve for this. We just use, right up here, we use this definition right up here, and we get what is called the finite difference time domain algorithm. So this tells you that the wave field at time t plus delta t, that is the future wave. This is the wave in the past. This is the wave in the present. And then this corresponds to differentiation. So we differentiate the wave of now. We use the wave of the past, and we get the wave of the future. All right, we need two things to start the iteration. We need the wave now, and we need the wave one step in the future. So we start the time at 0, and then we go forward. Now there's a way to, if you don't know the first wave and the second wave, you can use a source term, and I'll get into that a little bit later, but just suffice it to say that we can handle this. Okay, so this wave equation will have, if we use the finite difference model, this wave equation will have an error, and this is the problem. So here is an exact solution to the differential wave equation, and if we put it in, it's 0. We put this psi 0 into the wave equation, and it vanishes. But we put this analytic solution into the difference equation, and it does not vanish. And this is the error that we get. But we can make it 0. And the way we can make it 0 is we change this parameter here. This is where we talk about non-standard. We have a difference equation model, and we change this parameter a little bit, and you will have this term here. And then you will have an exact solution. So this will give you the solution of the differential equation and the difference equation are exactly the same. So here it is. So this is the normal textbook fdtd that you will see in many different books. And this is the non-standard version. So all that has changed is one parameter. Okay, you might notice, if you're observant, that this seems to work for only one frequency, but the reality is you can define it for multiple frequencies. That is, you can handle a range of frequencies by just taking a reference value of this omega and k, and they are related, as you would know, and then you can solve for several, maybe depending on the parameters, maybe 10 or 11 frequencies at the same time. Okay, so now let's go on. I won't go on too much, but we can introduce a non-standard model of the refractive index. So this is the non-standard model of the velocity, in vacuum, and then divided by the model of, and now the source, we have a source term here. The physical amplitude of the source and the algorithm amplitude will be different. And I have derived that, but I won't bother with the derivation. We can discuss it offline if you're very interested, or we have some references that we can give you. All right, so now let's move to the nonlinear wave equation. So this is what we want to solve if we want to understand wave propagation in nonlinear materials. And here, I must tell you that there is actually no analytic solution to this. There is only a numerical solution or an approximate analytical solution. So you really need a numerical method if you have a complicated medium. All right, so here's the standard model. And this sub tau is really the electric field at time step t. And then t minus 1, the previous time step. And this is the future. And we have to solve for this. And you'll see that you've got a quadratic equation. And that will have two solutions, and it will be very difficult. In the non-standard model, notice how we handle this. The square term is modeled this way. And then the double derivative of the square E field comes to this. Okay, so this is where the non-standard model uses a slightly different procedure from the ordinary FDTD, but it's very, very similar. So it runs on the same kind of computer. It won't take a lot more. It actually will take fewer time steps. And better than that, it's actually much more accurate. So here it is. Here's the nonlinear wave equation. Here is the standard model. And the standard model, the standard FDTD, is numerically unstable. So what is numerically unstable? It means that when you repeat an algorithm, when you iterate an algorithm, the answer will diverge from the true answer. Often it becomes infinity, but it may just simply be a very large error. All right, so here is our non-standard finite difference model. We solve for this. So here is our algorithm right here. So this is it. I won't go through all the algebra. Again, we put a source in, and I won't exactly tell you right now. This would take a long time how we derived all of this, but just to take it from me that we have done this correctly. This delta XP just means that the source is located at position P on our numerical grid. So here it is. Here is the computational model. We have a light source in the vacuum, and it shines. So this yellow dot here, and then the orange material is the nonlinear material. And then, so this here, it's right here. This is it. So this yellow dot is the light source, the nonlinear material, and then it shines into the material, and I propagated some number of steps, and then we look at in fact, here in this example, 2,000 steps into the material, and then as you can see, we get this highly nonlinear wave, and we can analyze it now using a discrete Fourier transform. So here are the parameters that I used. The index of refraction was 1.6. So if there were no nonlinearity, this would be a very simple sine wave or cosine wave. But we put in some nonlinearity. The physical nonlinearity is usually much smaller than this, but I made it rather large just so that we can see the nonlinear effects without going to too many time steps. If you had typical physical nonlinearities, this might be an order of magnitude lower or even less. You might have to go a couple of million time steps, but for the purposes of this discussion, I don't want to do that, and I don't want to worry about supercomputing, especially not online. So I put in an incident wave. The amplitude is 1.1, and the frequency is 1/64 of a time step. Now, one thing you might ask before I proceed here, I just want to go back a little bit. You notice that there is delta X and delta T in this. And you might ask, well, what does this all mean? I mean, we have time steps and space steps, but what are the dimensions of these? The answer is that Maxwell's equations scale. So if we want to talk about, for example, light waves, now the light wave has a typical light wave in the visible range might be 500 nanometers, the wavelength would be. And then the delta X might be 1/8 of that wavelength, or 1/16 or something like that. Here in the nonlinear case, I'm using about 64 time steps per, or space steps per wavelength. And then the wave period is tied to the space step. Again, this is another matter that a technical detail I won't discuss so much. So you would know the wave period in this would be probably picoseconds or something like that. And so your time step would be some picoseconds. Now, if I were discussing microwaves, where you might have, say, 10 or 11 centimeters, depending on your frequency, then your space step might be, say it's 8 centimeters. Well, then your space step might be 1 centimeter or perhaps 1/8 of a centimeter, depending on what you want to calculate. And similarly, your time step would be, say, 1/8 or 1/64 of a period, of a wave period. So it all scales. So everything that I'm showing you can scale depending on the frequency that you're using, whether it's light or microwaves or even radio waves, although I don't think we care too much about radio wave propagation in nonlinear materials. All right. So now I've calculated out what my wave looks like after 2000 time steps. And now I do a discrete Fourier analysis. So what is a discrete? You've perhaps heard of FFT, fast Fourier transform. Discrete Fourier transform is just a case where we can have any number of time steps. Usually in the fast Fourier analysis, we need a power of 2. So we can have, say, 64 or 2 times 64, 4 times 64, etc. But that I'm not looking at. All right, so what I've done is I've run this equation. I've run this for about 2000 time steps. And then I pick a certain region where the wave has stabled. I've turned on a source. So at a certain time, there was nothing. Then I've turned on the source. And finally, as it's coming out of the material, I'm looking at this section. And then I put it into a discrete Fourier analysis. And the first harmonic, this is just another fancy word for the fundamental frequency. So this is the frequency of my source. And again, I've used it in these units that are not tied to any particular frequency, physical frequency. And then I look at the second harmonic. There are other higher order sum and difference terms of higher frequencies, but I'm just going to look at the first and second harmonic. And why only the first and second harmonic? Why not the third or fourth? The reason is that then we're going to, first of all, it's a lot of work to do. And secondly, I'm not sure I would believe these results because now we're going into a very sparse gridding. But anyway, let's look at the first and second harmonic. And I've got a nice, I don't have an analytic solution. I have an approximate analytic solution. And it's called the low depletion approximation. I'm not going to, again, derive this, but I will give you a reference at the end of this talk. And so here is an analytic. This red line is the analytic solution of how the energy transfers from the fundamental wave into the second harmonic. So here's the first harmonic wave as we're going along, coming out. So we're just going into the material, we're coming out of the material, and now we're seeing this part. I'm looking at this part in the analysis, but I have I'm showing you the entire range. And this is why does the blue line, which is my solution, diverge from the red line, or why does it oscillate around it? Because I'm showing you the time dependence, whereas the analytic solution is not looking at the time dependence. All right, so the point is that you can see that it's a very good agreement. In fact, it's almost perfect agreement. It's following the analytic, the FDTD, the non-standard FDTD, is following this red line almost perfectly. This yellow line, let me just remind you, I should say orange line, just indicates the material. So I'm looking at what's going on in the material. And again, here are the parameters of what I've done. So there are 64 time steps per wave period in this. Okay, and so here here is the parameters that I used in the calculation. I've chosen a set of time and space units such that the speed of light is 1 in the algorithm, but you can easily translate this into physical units. So you get numbers, you will get your electric fields in terms of volts per meter, which is what you would want. So it's a very easy calculation. Now, we can extend this to 2 and 3 dimensions. Now, we don't have an exact solution to Maxwell's equations or the wave equation, but let me just tell you that in the ordinary FDTD, the error is proportional to this space step to the 4th power, kh. So it's basically h over the wavelength. So h is always smaller than the wavelength. So it's the space step to the wavelength to the 4th power. This is the space step to the wavelength to the 8th power. And of course, space step, the ratio of space step to wavelength is always less than 1. And it's usually at least 1 over 8, but more likely a little bit larger, in this case, 1 over about 64. So we're getting a and then look at here, we've got this 1,800. Here we've only got 2 to the 8th. So we have 2 to the 8th down here, 1,800. Here you've got 1/3 and 2 to the 4th. So you've got a very much higher accurate, or very much lower, I should say, error. Now in 2 dimensions and 3 dimensions, we would need to approximate the Laplacian a little bit differently. And I just suffice it to say, in say 2 dimensions, we would look at here is the position where we are. We would look to the left, to the right, to the up and the down. In the non-standard method in 2 dimensions, we use these diagonals and we combine them in a clever way. Again, we have some references you can look at, so I won't go deriving this completely. So we get a very small error. And now I'd like to just show you about the stability. The ratio of space step to time step times the velocity cannot be anything. In this case, it has to always be less than or equal to a certain value. So you could think of it as a speed limit on the numerical grid. So in 1D, the speed limit is 1. This ratio has to be less than or equal to 1. In 2 dimensions, well, there's a theoretical speed limit and a practical speed limit. And again, because you have more than just this wave equation, you have some other things to handle boundaries at the edge of the computational space. So there's a practical speed limit, but it's much higher in the non-standard methodology. Here it's 0.67, just 2/3. Here it's 4/5. So you can calculate, you have fewer time steps, so you go faster. In 3 dimensions, it's even more dramatic. Here the speed limit is the practical speed limit is 0.45. Here the practical speed limit is 0.7. So again, you can go faster and you also have this higher accuracy. And just to give you a little bit of how should I say, intuitive idea about how FDTD works, or actually about how the physics of light propagation works, you have a point here. This is where we are now, where the wave field is. We take information from the local region in the finite difference method to the left and to the right. And then we have from the time before, the time now, and we propagate forward to the future time. So information is flowing from a small region and then computes the future. All right, I won't go into all of this. I just want to show you some results. So we have exact analytical solutions only for a few simple things like a sphere and an infinite cylinder. So I'm showing you an infinite cylinder. And this is the scattered wave field from an infinite cylinder going into the picture. And so this is the theory, M-I-E, the name of the person who developed this theory at the early 20th century. Actually, his papers are published in the same journal of Annalen der Physik as Einstein's special relativity paper in about 1905. So here is the non-standard FDTD. Here is the analytic solution. And here is the textbook FDTD. And we've done this on a very coarse grid, just 8 grid points per wavelength in the vacuum. So in the cylinder, it's less than 8 grid points per wavelength. And so the standard misses this central lobe and it exaggerates. So we get a very good agreement. And I'll just show you a quick video of how good this agreement is. So this is the beauty of FDTD. You can see the time development as you compute. So if you really want to understand how the light is propagating or the microwaves in your material in real time or algorithmic time, but this gives you real time as well, you will be able to see. And now what you're seeing, the blue line is the FDTD solution. The black line is the analytical solution. And you can see that it's well, not completely exact, but it's very, very close. All right. So I'd like to just conclude. So we have a non-standard methodology to solve the wave equation, and we can put this into Maxwell's equations. I haven't done it just because it would be a little bit more complicated, and we can do this for the Yi algorithm. This is FDTD for the full Maxwell's equations. But you can I will, if you're interested. Again, we have references on this. And I just in closing, I just want to make one final remark. There are really very few problems that you can solve analytically. So here's a circular cylinder. We have a very messy analytical solution in terms of an infinite series of Bessel functions and Hankel functions. Here, a square cylinder. So you would have many structures that have no analytical solution. And even such a simple thing as an infinite square cylinder has no analytical solution. So these are some references that you can look up. And so this is, I can open now the discussion to any questions.
Hi. So this is a wonderful compact presentation, and you discussed. And if we can see 3 persons present, Sudeep Bharma, Rahul Haldar, and Noha Eq. So if you have any question, please put your hands. We can give you the microphone and also camera. You can directly ask question to Professor Cole. If you have any question, please just put your hands up so that we can mark you, give you the mic and the camera. Or you can also write in the comment section, chat section, the question if you would like to ask in text form. So if you like, we can give you the mic. If you like, you can also raise your hands, please. Okay. Since they are not raising their hands or they are not trying to speak, so we may proceed to the next part of the presentation by Dr. Saswatee Banerjee. So this is the part 3 of the online mini workshop on computational photonics. The part 1 and part 2 were streamed on December 6 and December 13. So this is the last part, the concluding part of the online mini workshop on computational photonics by Professor James Cole and Dr. Saswatee Banerjee. Now Saswatee Banerjee will make her presentation after sharing the presentation file. Yes.
Hi. Hello
Hi.
and welcome everybody to today's podcast. So as you already heard something from Professor Cole, and I introduced myself last time and again maybe. My name is Saswatee Banerjee, and I did my PhD in applied physics with specialization in optics and photonics. And I did my PhD, the first PhD in applied physics from Calcutta University. So that's where I met Dr. Devesh Chaudhary, and we again reconnected this year. And so this came to a nice little project. So we like to try to present, and the purpose or the objective of this podcast is to present a little flavor of the things, the computational methods, and the ways we employ in photonic design. So from that point of view, so I will try to give you a basic idea about the real life applications of photonics devices, and how you use these methods to design such devices, basically. So as you heard from Professor Cole, more like the finite difference based methodologies, and some of these methodologies that we developed. And we also, so I did actually use some of these methodologies to apply it to solve the photonic device design problems. And so here, what I'm trying to say in this thing, as you can see, that it's not just, I mean, at the design phase, you need to use these methods to actually design the device. You also need to use the modeling, basically, to be able to fabricate these devices. This is also a very important fact, because when you are dealing with these photonic devices, you see the dimensions are pretty small. They're kind of close to the wavelength, and especially in visible, that will be around in a nanometer range. That is maybe a few hundred nanometers range. So for that, when you are dealing with that, you have, I mean, the fabrication methods are very costly. So what you need is you need a very rigorous and accurate method to design and to predict the behavior of the device. And another thing that I have also seen myself, that is when you are trying to fabricate a device, you see the fabrication is not exact. You won't get, I mean, exact behavior from your fabrication. So things will be, you can expect that behavior will be different from what you are really designing. So you need to do simulations to basically fit back into your fabrication methods. So that's how it works. So that is where these computational methodologies are very important. So now I think, as I described in the last time, actually last podcast, basically, that what we are going to deal with here is light interaction, and light interaction with different media, light interaction with the different structures. And when light is, there is one thing is when light is propagating through homogeneous media, so it behaves in one way. And I think some of the, for example, the wave equation, for example, can be used to describe light propagation in homogeneous medium. However, there is, with nanoscience and nanotechnology, one thing that became possible is to create some artificial media. That is, you can modulate these refractive indices and material properties in a nanometer scale, basically. That is possible. So now when you are dealing with this kind of medium, you need a little bit different. You need more, like, you need to solve the Maxwell's equations depending on the situation. So you can definitely use some structural symmetry, exploit those kind of things. But basically, you need a rigorous method. That is, you need to solve the Maxwell's equations. So here we are dealing with interfaces between different media. And these interfaces can be structured, it can be unstructured, but the interfaces are something that we need to think about. And when we are dealing with the light propagation across different interfaces, one thing that matters is the electromagnetic boundary conditions. That is something that we need to talk about. So in my last presentation, I mean, the last podcast, I did little bit talk about the photoluminescence and also the luminescence behavior, basically. That is the emission, light emission behavior in active media. In fact, so also the electroluminescence that is we are seeing in light emitting diode, and how you model such behavior in optics. So I little bit discussed that. So I think there is another type of device, of course, the light absorption device, which you see in, say, even solar cells and detectors, etc. So this time, I mean, I decided to little bit go into the photodiodes and just see what is there. So it is kind of, I mean, interesting because it's a real life problem, and that's where you need a lot of design actually to do it. So now there, as I said, that another thing that is also very important to understand, again, you are not doing all these things in really real time, because in optics, we really don't measure everything in real time. We do it in frequency domain. Basically, we measure things in frequency domain, and real-time interaction we don't even observe. However, fdtd, or as Professor Cole was discussing about finite difference time domain, so this has become a highly effective method to deal with complex structures, different kind of structures, basically, because this can be implemented more, I mean, in a stable fashion. And as I was talking about the electromagnetic boundary conditions, so the boundary conditions become complex. And so this thing, this algorithm has the thing is, once you start, the time marching starts, it implements those boundary conditions automatically. You don't have to do very much. So that is one good point about this algorithm. And that's why we use the finite difference time domain actually to solve a host of different types of problems. So now coming to the photodiode thing, what I'm going to little bit, as I said, the purpose is to just give a flavor of what this is all about. So we are very familiar nowadays with the digital cameras. So what the digital cameras do, and in fact, if you are doing optics, if you know this domain, even before the digital cameras were introduced, when we were students, actually, at that time, there were no digital cameras, but there were photographic films, definitely. And we did actually study the characteristics or the responses of photographic films. And you can see that even there is a range issue, basically. How the photographic film responds to light, that is a very important part of photography, basically. So in case of digital cameras, now what happened is that, okay, you do have a camera lens, and then the recording plane actually is electronic. So, optoelectronic, I should say. So that means the recording plane you use some photodetectors there. So there is, of course, you possibly, if you are doing a lot of experiments, for example, you are very, accustomed with this charge coupled devices that is still used. And for high-end purposes, definitely charge coupled devices are used. Now, for the simple, the cheap, for example, our smartphone applications, the CMOS image sensors are used, in fact. And these are, in the recording plane, if you look into the recording plane, you will see that there are these pixels arrays. This is a pixelated plane. And the pixel pitch and number that determines the resolution of your photo, finally. Now, these things, at this moment, as you know, that there is a lot of push towards making the high resolution, okay, in photography. So for high resolution, what you need is you need to make the pixels smaller and smaller. So when the pixel becomes smaller and smaller, then it is also becomes more like diffraction limited, and the behaviors that are more wave phenomenon and the behavior that you see with electromagnetic behavior more, shows up, basically. That's what I'm trying to say. Now, here there is another little interesting thing about it is this dynamic range and image contrast, etc. So what we are talking about here is the range of luminosity in the scene. So if you have a very bright and very and less bright regions, what can happen? This is something that we all saw, basically. So what can happen is your scenes have high brightness region and low brightness region. So you can lose some of the details in the low brightness region. So I will show you a very simple picture. This is our picture. Okay. So I just show you because this is something called, you can see the challenges that I'm trying to talk about. This is, Christmas lights are on around this area. So in the night, this is all night scene I'm trying to picture. This is with smartphone, basically. So you can see the challenges here because there's a lot of light. The light source is very bright, and then of course we are not so bright. So you are not going to really see the subject so well. So now there is more. It is possible to make it more, clearer so that you can see the objects that are in low brightness area. One of these, this is called actually high dynamic range. That is, you are covering a higher range of luminosity. Basically, that's what you are doing. So now to do the high dynamic range, in fact, you do it with commonly used technology by a lot of companies is something called multiple exposure. They combine multiple exposures. And again, this is actually not done in optics. This is where the optoelectronic part comes into effect. Actually, a lot of these things are done in electronics. So this multiple exposure is done in the electronic side. But in any case, this is one of the way to actually enhance the dynamic range or increase the dynamic range. So now I will more look into the optics side of it. So one of the things that comes into effect here, that is, if you have this, I will talk about this CMOS image sensor. As you can see, the name CMOS, that is, it is actually done in this complementary MOS fabs, and so because it can be, I mean, fabricated in that kind of fab, so that's why it is a CMOS image sensor. Now, in color photography, and of course there is a color effect, and then I also want to say that there are different types of these structures, right? One is the front side illuminated, then the back side illuminated. Now, without going into too many details, what it is with front side illuminated, I mean, if you are interested in details, we can talk about the details later. Offline, we can have a conversation about this. But the front side illuminated, what happens is it is difficult to reduce the size. As I said, that because of this push for resolution, high resolution, so you need to reduce the size of the pixel, but that is something pretty difficult to do with front side illuminated configuration. So, I mean, for smaller pitch size, it is that backside illuminated technology is preferred, basically. So if we go into the color representation, as we know that in many, I mean, displays, basically the colors, I mean, different colors and shades and all that is represented by three primary colors. That is the RGB, basically. So what will in general, I mean, in the simplest form, what happens in a pixel, if we look at the, I mean, a simple concept of the pixel, is you have at the center, you have a PD, a photodiode, basically, and this is a silicon photodiode. And so then you have, because this is interesting, here the material consideration comes in. As we saw, for example, in the last podcast, I talked about light emission. When we are talking about the light emission, certain materials, we use certain materials. Here, though, in absorption, you are using the silicon. The reason silicon is used, silicon is a good absorber, especially in visible light, because it has something to do with the material's band gap, basically. So it has this band gap, which is convenient, and so silicon can be used very well in light absorbing devices. This is something a little bit different compared to the light emitting materials, where you need to have the direct band gap materials. In silicon, actually, this is not direct band gap, this is indirect band gap. So basically, it can be used very well in absorbing light absorbing devices. Now then, again, as we understand, silicon actually has a high refractive index. So you see, as we discussed about the interfaces, so when you are coming to the interface, light is coming from outside, and it will, what happens is we need to separate, because of the color representation, we need to have the different filters. Say for primary colors, we have this color red filter, green filter, and blue filter. And each filter will have their transmission in red, green, blue. But these transmissions actually have one thing, this is important to understand, is when I'm saying red, green, blue, it doesn't mean single wavelength. They have a broad band of transmission wavelengths, basically. It transmits over a broad band. Normal color filters, because normal color filters are made from, either pigments or dyes, etc., are used to make these things. So it has a broadband response, basically, transmission. These are very important concepts when you are trying to design these things, because of this broadband transmission, it can cause some crosstalk between the different pixels. When you are making a pixel array in the recording plane, you have to care about the crosstalk between different pixels. And actually, this transmission pattern of the filters can contribute to the amount of crosstalk that is coming in, basically. So these are the little things that will come into your design considerations. So here, so basically, this is one, basic structure. Now, there is one more element that is very important when we are talking about this kind of light absorbing devices, especially small devices that absorb light. You would like to capture as much as light possible, right? Because you want to increase or boost the quantum efficiency or optical efficiency, that is the amount of light that is absorbed in the photodiode. So here, if you look at the left-hand side, this is a very basic configuration of the cross sections of this pixel. So you can see the silicon photodiode, which is at the center of it, and you need this AR is actually anti-reflection. As I was telling you, silicon has a high refractive index, so and we need to care about, light loss from the interfaces. This is another very important consideration here. So you do care about an anti-reflection layer. And then you do have the color filter layer on top. And then another very important concept is this microlens, because without the microlens, if you think about it, actually you need an in-coupling element to get light from different directions, and that to come in and to basically focus it or concentrate it into the 3D. So you have this, microlens. Now, what I'm trying to show here that, in the design, you can, where do you start? How do you start here? Now, I have this little equation. This is, you all are very familiar because it's a high school level thing. That is, if you know the radius of curvature, if you know the refractive indices, you can calculate the focal length, basically. So if you do calculate the focal length, but there is a little problem. This relation only applies, paraxial optics or macro optics, etc. So this might not really apply to a microlens or a microstructure like this. So ultimately, yes, you do have to do a rigorous calculation and to see that where the light is really focused. And it will depend on the microlens parameters, how this light is focused, where the light will be focused. Now, this is another very important concept in this design, because it will change, it will have a huge effect in how the optical efficiency, it will affect the optical efficiency, that is how much light is actually absorbed in the silicon photodiode. And another thing will be, again, the concept of crosstalk will cause a lot of trouble because the light can just go in many directions. This is where actually a visualization like this helps a lot to see where the light is going, really. And you need to manage the way light travels inside the pixel. That's the goal of the design, in fact. So you would like some strong focusing, and you would like to, as I said, you need to really manipulate and manage how the light propagates through this medium. now, okay. So now the point is, this is where I will show you some amount of optical design, how we are doing. And this is here I'm using a commercial software and very, popular software, etc., just to show, because this is in 3D, this is done in 3D. You can do it many ways, but the thing is, this is where the power of fdtd is, I think. That is, if you can see that it is showing in real time how the light interacts with different media, different interfaces. If some light is reflected back or some light is transmitted in, you can see that. And that is, I think, is very, important about finite difference time domain method, that you can study the material in real time. You can study the structure, a complex structure like this, in real time. So here what is happening is you have a light coming at 540 nanometer, which is just green, and it is coming at an angle, and you can see how it is behaving and how it is interacting. That is, the light, it can only pass through the green filter. It cannot pass through the red filter. As we saw, if we run it once again, we can see that, which is, just understandable, but that is what is happening here. Let's look at it a little bit more. Or it's not doing it. Okay, so what it is, so here, what are the input parameters? So this is a typical, optical design flowchart. So here we do have the, these are the Maxwell's equations, as I think Professor Cole also discussed. So these are the main equations that are solved in finite difference time domain method. And then, most of the problems that we deal with in this particular case, for example, there is no nonlinearity involved. So the materials that are involved, there is no nonlinearity. However, there is a lot of dispersive characteristics, dispersive material properties are involved. Each layer has its very dispersive properties, and then it becomes pretty complicated. The whole implementation of these Maxwell's equations become very complicated, and you do need to take care of this epsilon, or the material dielectric constant, basically, and how it changes as you change the wavelength of light. And in the input parameter side, you have the layered structure, you need the materials, you need the thicknesses, and then you need the incident light. Of course, you need to know whether it is narrow band, whether it is broadband. How much normally you are going to deal with broadband light. And then the incident angle, because all the responses will depend on the incident angle, the beam type, what kind of beam you're going to use, and also the coherent state matters, because since the light, in this particular case, real life story is you have more incoherent light coming in. So you need to do a sum over different angles, different coherence, different polarization states, etc. So actually, in this field, the geometrical optics or ray optics used to be employed to calculate these characteristics, the responses. However, now that the pixel is becoming smaller and smaller, there are papers which actually compare with how the ray optics results and finite difference time domain simulation results, how they compare with each other. And actually, these rigorous simulations give you better results. There are some, results that show, and some papers that show that. So what you are getting from this kind of simulation is actually the optical efficiency. That is the power that is absorbed. And here on the right-hand side, this is something that depends on, this is something that depends on the absorption, silicon has a complex refractive index and dispersive complex refractive index. That is, it has the imaginary part. So the imaginary part will decide how much light is absorbed basically inside the material. So that using that, you can calculate the power that is absorbed. And then the number of photons, when you are trying to convert it to the quantum efficiency, so the quantum efficiency will be proportional to the optical efficiency. That is the amount of power, light that is absorbed. So here there are a couple of considerations, as I was trying to explain. That is, you need to care about the angular response. That is, as the light coming in, the incidence angle, and how the response changes with that. And then you do need to care about the crosstalk. That is a very important concept in this domain. So, and then the simulation model, depending on what you are trying to do. For example, especially when you are dealing with crosstalk, then the single pixel models don't work really. So you have to take a whole array of pixels, in fact. So that makes the whole thing very complex. I mean, compute intensive, basically. And a lot of these things that you need to do it in 3D. So that is also something that adds to the whole burden, a computational burden. But there are much more details. So, if anybody is interested, one day we can go into that and discuss more details in this field. And now, what happened? So in summary, I will just say that there are different types of computations, rigorous and sometimes not so rigorous, are needed for effective design methods, design technology, or design flow, basically. So, and it's not that you start with rigorous simulations, because it can be very taxing sometimes. It can be compute intensive. So what you do is you start with maybe first principle designs, etc., and which can be done. You can do it yourself. Actually, you can develop certain programs and calculations, etc., and you can do it yourself. And finally, of course, you have to do the rigorous simulations and very, powerful simulations, etc. But you can also do the simple calculations, and it's really intuitive, and it gives a lot of insight into the underlying physics of a device, how a device really works. Thank you very much for listening.
Hi. Thank you, Dr. Banerjee, for completing that lecture so nicely for this application, devices application. So maybe if some questions are raised, any query by now, although 17 or 18 people registered, 4 persons appeared, 1 person listening. So if you have any question, we can give you the audio or microphone. Please ask the question. So since you are patiently attending this for more than 1 hour, we allow you to talk or video. Please, Noha. You can ask your question or raise, or you can also add it to the question answer mode. So if you have any question, you can unmute your mic and ask us, or you can also type in the question answer section. We have given you the audio and the video permissions. Yes, please. You are already here. Now you can unmute and ask your question. or any comment or anything, because you are listening it entire part 3. So if you have anything, please ask here, or you can write also in the comment section. You can, of course, ask later also to Dr. Banerjee and Professor Cole on LinkedIn, but this is an opportunity you can directly talk to them and ask. So if you don't have, okay, I have one I have got some interesting things you have shown that means the CMOS camera designers and manufacturers, they do some this type of calculations and things for designing their image sensors.
Yes, they do. You need a lot of, real rigorous and serious calculations and simulations. There's a lot of, analysis that goes into this design.
And the CMOS sensor inside, I have not opened or I have not seen that. So that means on every pixel there are some a designed micro lens sort of thing.
Yes, you do. Actually, this micro lens is not just micro lens, a single micro lens. I showed a simple picture here, but you have to deal with micro lens arrays, basically. And when you are dealing with those micro lens arrays, then again, there are ways of how you really array them, basically. So there are details there. A lot of design goes into how you array them. And as I mentioned from the beginning, that all this process, in fact, it goes hand in hand with your fabrication side, fabrication results, and then you go characterize these things and you get the results, you measure the results, and then you go on feedbacking from the simulation side.
That is very means the potential applications are there. So people are 1% just joined. So I have one question, means it is not for this part, but maybe if Professor Cole and Saswatee comment on this application of your non-standard fdtd to microwave propagation, or the people who are doing in antenna designs. So if you give some hints to how your technique also can be applied to them.
Okay, so have you? Can I see? Okay, so the FDTD that I showed is independent of the wavelength and the frequency. So what I mean is that Maxwell's equations and the wave equations scale. So, for example, suppose that the important thing in any FDTD calculation is the ratio of the space step to the wavelength. So, for example, suppose the wavelength is 800 nanometers. This would be in the infrared or near infrared, let us say. All right, then you would want to choose a space step that is at least or smaller than 1/8 of that. But let us say it's 1/8. Okay, so now if you're in the optical range, the infrared, and the wavelength is 800 nanometers, then you might choose a space step of 100 nanometers. Now, in the algorithm, you would write delta x equal 1 in the algorithm. So now but now when you go back to make physical connection with real light, now you would put this delta x into your physical calculations, and you would know that this is light. Now, suppose you're using microwaves, and let's say the wavelength is 8 centimeters. Now your space step would be 1 centimeter. And again, you can go and put this in, and your time step will be proportional to the space step. So then as I mentioned, that the time step must be 1/8 of the or less than that than the space step. Okay, so from this, if you know the space step, you know the time step, and from there you have the physical time in picoseconds or seconds, or maybe microseconds, nanoseconds of the time step. And now you can put this in, and you will have the connection to the physical wavelength, the physical frequency. And what about the amplitude? You can just take the amplitude in your algorithm to be 1, but now you say 1 unit of amplitude in the calculation is say 5 volts per meter, whatever your physical amplitude is. So you don't have to complicate your algorithm with all these physical units. You do the transformation later. The only difference in going from, say, optical light, from light waves to microwaves, will be that your physical parameters might be different. For example, if you're dealing with the permittivity, it will be different at the microwave frequency than at the optical frequency. So in other words, your index of refraction or permittivity. And the same might be the case with magnetic permeability, depending again on the kind of material. So you would have to adjust those parameters according to the frequency. But once you have done that, then the calculation, the methodology is exactly the same, whether you're in the microwave domain or the optical domain. So that's
Yes.
how I would answer the question. Thank you.
Thank you for the hints, and that means your technique can be applied to any electromagnetic waves, and the parameters has to be.
I think you are muted.
Is it?
No.
Is it not coming? Audio? Can you? Can't you hear me?
Sorry, it's you are not muted. I was keeping my microphone.
Okay. So that means your technique is can be applied to any electromagnetic waves, and only the parameter has to be properly selected, that where it propagates and where it applies. So
yes, that is correct. Right.
yes. So can you give some concluding, because this is the part 3 and the final episode of the mini workshop on computational photonics, your techniques. So can you just conclude that whether it is possible to make a one workshop, say 1 day or half-day workshop on computational photonics and microwaves?
Yes, we can do that, but there is one question here. Maybe we can answer that question.
Yeah. Are we broadcasting, or has the broadcast ended?
Or if you wish to discuss in confidence, that also we can do. And whatever it is possible to disclose in the public, you please do. Because we are planning to.
Do you want to answer this question?
Right. I think we could say that we would. I think we.
No, there is a question.
Oh! Could not attend a major part.
I see. Okay. Let us give her the permission. Okay. Sonal.
Water medium. I can answer.
Yeah.
Yes. Please.
Let me answer. I'll answer it verbally then. Okay. So you want to know about modeling the propagation of light in the underwater medium. The underwater medium is no different from any other medium, except that the index of refraction is different. So if you have, I assume that perhaps in a realistic underwater medium, for example, the ocean, you might have a lot of small little particles. Maybe you have some fish in the water. Maybe you have some other things floating in the water, maybe plankton or something. The other thing that you would care about is the surface of the water. That's the boundary between the water and the air. That might be, the surface might have waves in it. So you would maybe want some sort of model of the real surface. But other than that, the modeling is the same. You would have a light source in the underwater. Maybe you're shining some light in underwater, and the light is shining through the water. You propagate through the medium. I presume that if the water is a uniform medium, except for the surface, and maybe the bottom you don't care about because it's going to be absorbed. So what I would do is I would model the surface only, and I would have the surface on the top, the propagation of the water, and then underneath the region of interest, say you're at say 100 meters deep. All right, so the surface would be quite far away relative to the wavelength. So you could just put simulate an infinite boundary on the water. If the source of light is closer to the surface, then you would care about that boundary between water and air. So you would simulate that. You would have a small region above the surface that you calculate, and then beneath you would just have a boundary that absorbs everything. So it would be rather straightforward. It would not be at all difficult.
There can be, it will depend on the particular problem, but I can imagine, for example, the refractive indexes may not be the constant, or it can change with time. I'm not sure exactly what is the application that you were talking about, but it can change with time. And because there can be waves, I think he talked about.
If you're near the surface, there would be waves, but I think if you're beneath the surface, more than a couple of meters where the waves don't reach, I think you can just make a model. Say there's some random plankton in the water or random fish. You can model those very easily, scattering off of the fish, scattering off of the plankton or whatever else might be in the water. That would be straightforward. We've modeled, for example, colloidal particles in thin films. And you have these particles with one index of refraction, the film has another. So this is where fdtd is very useful, because you don't have to explicitly put in all these boundaries. It's automatically taken into account as the algorithm propagates. So in the water, it would be no different. It would not be difficult.
Yeah, actually, I did see some modeling around, with small organisms, actually. I think in this ACES, the last ACES, there were some papers, some guys were doing some modeling with small organisms, how you represent it in this finite difference time domain method, basically, to study those things. So yeah, you can make some models of the medium, and that will be the major part of the work, maybe.
Okay. Yes. So please conclude that three-part mini workshop on computational photonics you have delivered. So please comment about, say, how can you make this a half-day or one-day workshop on computational photonics, if it is possible to disclose here, or we can also any other comment, like concluding comments, if you wish to give.
Yes, if there is interest, so then we can go forward and we can do an not a long time, but maybe 2 hours or something, we can do a little discussion. Now, I think sometimes, I mean, in person is far better than doing things online. However, in person means if we are going to be present in some place, then if people are joining from another place, it's pretty difficult for them to join. So that kind of issues can also happen. But yes, we will be very happy to do this kind of thing, especially if there is interest. And also you can get in touch with us through our website, through LinkedIn, if you are interested in this and in more detailed discussions about these issues.
Okay, thank you very much for giving this three-part uh, online mini workshop on computational photonics. So that is the end of the session. So we'll end the live streaming here. Okay.
Thank you. Thank you very much for attending and listening.
Yes, thank you.